Alright, so starting with chapter 4, mole ratios in chemistry. There's two main mole ratios that we use in chemistry. We have the element mole ratio, which is an element within a single substance. An example of that would be calcium phosphate, and if I asked you, well, how many moles of calcium phosphate are in 1 mole how many moles of oxygen are in 1 mole of calcium phosphate? You'd say, well, only look at calcium phosphate, look at the formula, and I see that there's 2 times 4 here, so there's 8 oxygens, and that means there's 8 moles of O in every 1 mole of that substance. So this is an example of the element mole ratio. It's just one element within a substance. And of course, you can flip that ratio if you need to, cancel units going the other way. That's not our building. If it is our building, we'll go down in flames. I'm not going to stop lecturing now. So the smoke will start to come in, and it's a mole ratio. Can you see this? Okay, put your gas mask on. We'll get to our lecture after we get the gas mask on. I'm pretty sure it's the building next door. All right. So mole ratios, element mole ratio. Okay, but then there's also the stoichiometric mole ratio, and that's when you have chemistry going on. And then for this particular example, for every 1 tetraphosphorus decaoxide that reacts, I consume 6 moles of water, and so forth. If I wanted to write another mole ratio from that, I could say, okay, I've formed 4 phosphoric acids for every 1 P4O10 that's lost. And of course, I can flip the ratios if need be. So does everybody see the difference? This is just big picture stuff. Can everybody see the difference between element mole ratio? It's just moles of an element within a compound versus moles of a reactant relative to a product, right? It's a different mole ratio, but nonetheless, 2 main mole ratios in chemistry. Okay, so there's general steps to solving any stoichiometry problem, because when we're dealing with chemistry now, we can do stoichiometry.